Hello, folks. I'm Tom Coughlin. I'm the chair of the IEEE Santa Clara Valley Technology History Committee. Today, we're going to have a talk on Ethernet's emergence from Xerox PARC 1975 to 1980. Just a little bit about our group and then a quick introduction before we go on. So we were formed by the IEEE Santa Clara Valley section in 2013. We've had a number of talks on interesting historical topics since then. We're an IEEE local group. Our webpage is siliconvalleyhistory.com. And you can find presentations and video of our talks available at this URL here. We're looking for new meeting technical history programs. That is ideas for future webinars or perhaps live meetings. If you have an idea, please contact me, Tom Coughlin, at tomcoughlin.com or Brian Berg at brianberg@gmail.com. The moderator of this session is Geoff Thompson. He's a very early user of 3 megabit Ethernet at Xerox PARC. He supported Gary Starkweather's pioneering work on laser printing. He moved to Xerox system development in 1981, working on workstations and the Ethernet. He's participated ever since then in IEEE 802.3 since 1983. At that time, he's chairing the Repeater Task Force, among other work. In 1988, he worked at SynOptics Communication, later Bay Area Networks or Nortel, and was doing standard works full time. He's a chair of 802.3 from 93 to 2002 and still continues with active participation in 802.3 and 802 governance. And with that, Geoff, take it away.
Thank you, Tom. Welcome, folks. As Tom said, this is the Silicon Valley Technical History Committee, and there's our pitch about ourselves on the bottom. This afternoon's talk is sort of the middle section of the life of Ethernet. It's after the, well, I'll talk about that in a minute. But before we get started on that, I wanted to pay special tribute to 3 of the major personalities in Ethernet hardware development. All 3 of which had a lot to do with the analog and cable side of Ethernet. The late, great Ron Crane, who was highly instrumental in getting the whole implementation and standard off the ground, died in 2017. And earlier this year, we lost David Boggs and Tat Lam. David was the co-inventor of Ethernet with Bob Metcalfe, and Tat Lam was the developer and supplier of transceivers during the early life of Ethernet. With respect to questions, you can put them into the Q&A tool anytime, but the normal expectation is that they will be addressed at the end. Some might be picked up and answered before that, but basically we're going to have a Q&A at the end. Our panelists today are Bob Metcalfe, co-inventor of Ethernet, Dave Liddell, who was head of the Xerox Systems Development Division, which was the development organization for Ethernet and related product lines, and Gordon Bell, who was VP of Engineering at Digital at the time of the DEC spec. Bob was the co-inventor of Ethernet in 1973, along with Dave Boggs. And it wasn't just a lab toy. It was spread throughout PARC, Xerox Research Facility, and then the rest of the Xerox R&D community during the 70s. With networks between them, it stretched from Fuji Xerox in Japan all the way to Welland Gardens in the UK. So we had an early internet of Ethernets that went halfway around the world. Bob really became the relentless promoter of Ethernet, both inside Xerox and externally, most noticeably to the public as a founder of 3Com, which promoted Ethernet to the public and throughout the industry. In his many activities since then, he remains Mr. Ethernet above all else. And he is a fellow of the Computer History Museum. David worked in research at Xerox PARC at the time Ethernet was invented, where he provided some key elements to the first Ethernets, particularly the hardware to attach to the cable. In 1975, he became the head of a new division, which was created to productize the whole environment of the Alto, the Ethernet, laser printing, networking, and office software. It was a huge engineering effort on the order of 250 engineers at its peak. And the first result in November of 1980 was the announcement of network servers, file servers, print servers, and gateways. And then later in 1981, the announcement of the Xerox Star 8010 professional workstation, which was an all WYSIWYG, all icon based large screen workstation, very highly oriented to the 10 megabit product speed Ethernet. Later, he co-founded and served as CEO for Metaphor Computer Systems and was president and CEO of Interval Research. Since then, he served on the board of many corporations, as well as the Santa Fe Institute and SRI International. Gordon was a very early employee of Digital and later became vice president of engineering there. He was instrumental in the decision to choose Ethernet as the network for DEC for its promotion as an open standard. Among his activities, he had a stint at Microsoft Research, but his real claim to permanent fame was founder of the Computer History Museum in its Boston incarnation, and then he was instrumental in bringing it to California, and he is a fellow of the Computer History Museum. Oh, we also have some significant contributors who are participating here today. John, if you can turn on your camera so we can see you. John Shoch, can you give us a 1-minute resume for yourself?
Sure, thank you, Jeff. Just very briefly, my background goes as far back as when I was an undergraduate at Stanford, and I took a class that was taught by a guy named Alan Kay, and I used to argue with him a lot, so he offered me a summer job at Xerox PARC, and I stayed for 14 years. I started out working on the Smalltalk project, doing some software on early bitmap graphics and other things, and on data general novas. And as the Altos came along, and as Metcalfe and Boggs were developing Ethernet interfaces, in the classic Tom Sawyer handing out paintbrushes, I sort of got recruited to do a little file transfer program to see if we could connect machines, the Altos running BCPL and Altos running the Smalltalk environments. This is my first introduction to networking. I've told people it was a fool's errand to do IO control in a slow interpretive language, but I learned a lot. I spent more time then with networking and PUPs. Probably the major single contribution is along the way, I spent a couple of years doing my thesis work on analyzing the actual performance of an Ethernet and demonstrating that in fact it could have high performance under high load, and we had 90 machines banging on it and a bunch of other things. And after that, so while I was doing that, a lot of the development of the second generation machine was being done by people you'll hear from. And probably because I'd come off the writing of my thesis, I got drafted to really be the editor or consolidator. I can't say I wrote all of the very first draft of the DEC spec, which got handed off to other people who were smarter and more knowledgeable than I was. And I went off and did some other things and later came back to Palo Alto and the Office Systems Division and other things. But those are the key highlights.
Okay, moving right along. Roy, if you could introduce yourself and briefly say what you did.
Hi, I'm Roy Ogus. I I first joined the Xerox SDD team in March '77. I was working for Bob Metcalfe at the time. I actually came from Stanford University, where I was working as a postdoc at the time. I was actually hired on the team, which was tasked with the development of the Star Workstation product. Now, of course, the Ethernet subsystem is part of that overall system, although at the time we called Ethernet Xerox Wire. You'll hear more about that later. So my initial task when I started work there was to generate the Xerox Wire specification. And following that, I worked on the early product Ethernet and Xerox Wire controller development. I actually continued my career at Xerox until 2006. I worked in many different roles in technology areas over the years. In 2007, I moved to Adobe, where I still work today.
Thank you. Robert, you're next.
Thank you, Jeff. I'm Robert Garner. When Bob Metcalfe hired me in July 1977 to join his communications group in David Liddell's system development division, which we call SDD, for everyone who's wondering about those funny three letters. At the time, we were actually physically co-located with Xerox PARC, overlooking the Bay Area in the hills of Palo Alto, California. The folks there at Xerox PARC had designed 4 years earlier the Alto personal computer on my right here, and the 3 megabit Ethernet, which we'll be covering today, Metcalfe and Boggs. In SDD, I co-designed the 10 megabit Ethernet adapter and designed the CPU, the central processing unit, for the productized version of the Alto, the Dandelion, or that's the hardware, the Xerox Star professional workstation. After 2 years working in Lynn Conway's VLSI group at PARC, I joined Sun Microsystems, where I led the group that defined Sun's SPARC architecture and co-designed the first Sun Unix workstation, the Sun 4200, which primarily went to engineering and scientific applications. And later today, I'll be talking about all this hardware, and at the end, I'll be co-fielding the questions with Jeff.
And now it's time for Hal Murray.
I was the software guy. My role in life was to generate lots of packets and kick the tires and find the glitches. And I started out by porting the BCPL networking environment on the Alto to the Mesa world. And when the guys finally got the 10 megabit hardware ready, we had the software all ready to go.
Thank you. Bob Belleville.
I'm Bob Belleville. I joined Xerox SDD from Stanford Research Institute to work for Bob Metcalfe in late 1977. I started the Dandelion project and took over its management of the hardware in 1979 when Bob Metcalfe left to form 3Com in '79. Ron Crane and I worked on the early technical aspects of the DEC spec. In 1982, I joined Apple and directed engineering of the original Mac, laser printer, and AppleTalk network.
Thank you. Dave Redell.
Hi, I'm Dave Redell. I was one of the early outside hires to Dave Liddell's new SDD group. I joined Xerox from MIT in August of 1976 to work on the new operating system we call Pilot. And I worked with Paul McJones to design the file system, virtual memory, and with the Mesa language group on the concurrent programming features, what we would now call threads, but the term hadn't been invented yet. Then in 1980, David Liddell asked me to represent Xerox on the 3-person committee that produced the final version 1 spec, that is the Blue Book. After the version 1 Blue Book was released, Bob Prentice took over the Xerox role in that sort of troika of spec writing people, and I started another group to do higher level distributed servers and protocols like email and the clearinghouse being our precursor to the Internet DNS domain name system. So while I did play a central role in the actual writing of the spec, my role was really to help push a much longer Ethernet design and specification effort over the finish line.
And then our last on the list of contributors, and the only one not from Xerox, Rich Siefert, who was at Digital. Rich?
Thank you, Jeff. Hi, I'm Rich Siefert. I came up through Digital Equipment working on the original VAX, the VAX 11780, and the Advanced VAX group moved up to work on the Ethernet project. I was known as the person at DEC who dealt with all of the states between 0 and 1. And so as such, I became responsible for the physical channel design of Ethernet, the cabling, the transceivers, the signal budgets, the encoding and decoding. And I was one of the 3 co-authors of both the version 1 and version 2 DIC spec, along with my compatriots at Xerox and Intel.
Thank you. Now, moving right along, if I can get back to my slides. New slideshow. So this wonderful spreadsheet that Mr. Garner did is the generations of Ethernet during its first decade. And if you can see, it went through quite a few, which are distinguishably different.
We can't see it, Jeff.
Ah, well then, I'll try again. I didn't learn how to start sharing. No. Can you see it now?
Yes.
Oh, goody. Everything I said before. It's an eye chart. We can make this available afterwards because it's sort of interesting, but the major thing of interest is the number of iterations that things went through, going from Metcalfe's start to the time we got it into 802.3. But roughly, we're going to break up the talks for the first 5 generations of the spec, and it's going to be done with Metcalfe briefly covering the experimental and then getting into the Xerox wire and then carrying on from there. And I'm going to quit sharing now and turn it over to Mr. Metcalfe.
So I shouldn't be offended that you put very brief by my name. Do I needed to be reminded about that, do you think?
Well, I didn't want this to become a large treatise on 3 meg Ethernet. We're supposed to be talking about 10. So tune yourself accordingly, Bob.
I am so tuned and delighted to be here and grateful that you've created this reunion. It's been great preparing the remarks for this. I got to meet y'all again after many years. What you're seeing on the screen now, I hope, is a diagram from the Ethernet Invention memo of May 22nd, 1973, showing the Ether network.
We can see that.
Oh, good. So before that, I spent 1970 through 72 putting MIT and Xerox on the ARPANET, which I think of as Internet 1.0. But then in 1973, CSL, Computer Science Lab at Xerox, decided to build what is arguably the first personal computer, modern personal computer. Let's call it, it was called the Alto. And because I had been the networking guy at MIT and was now the networking guy at PARC, I lucked out. And I got to design a network to connect the first building, I believe, full of personal computers, a personal computer, if you can believe it, on every desk. And it was out of that effort that Ethernet was invented. Dave Boggs and I built the first Ethernet, and the four names on the Ethernet patent are myself, Boggs, Butler Lamson, and Chuck Thacker, may he rest in peace, and may also David Boggs rest in peace. So we invented this Ethernet, and you'll notice it has a shared cable, and then these are Altos tapping into that cable, and this is the diagram from the Ethernet memo. And now let me tell you the three key technologies that we employed in the this PARC, the first Ethernet. Later I'm going to tell you the real three, but these are the first three. The first thing we did, thanks to David Liddell, who suggested it, we chose a thing called the Gerald tap, a method of puncturing and connecting with a coaxial cable. So this coaxial cable became the shared medium of the network. So we had hoped to be using as few wires as possible, and the number we ended up with was 1. We couldn't use radio because the radio modems were too big. So we did have to use one cable, and there it is. And the Gerald tap allowed us to add a PC to the network without bringing it down. You would just puncture the cable and connect rather than cut the cable and insert successive machines. The second key technology was the Manchester encoding. It was an on-off coding. Either it was driving the cable to its voltage, or it was letting the cable go. And we had two benefits from the Manchester encoding. One is the clock. This Ethernet didn't have a central system clock. The clock became part of every packet, and the Manchester encoding, on, off, on, off, off, on, off, created the packet, the clock that shifted the packet into the shift register of the receiving station. And then the third key technology is AlohaNet. We needed a way for the attached stations on this network to take turns. And we didn't want to run another wire, so we had to figure out how to do it in band on the shared coax. And we borrowed a technology from the University of Hawaii, Norm Abramson, may he rest in peace, his AlohaNet randomized retransmissions, which we suitably modified for Ethernet. AlohaNet was a WAN, but because we were doing a LAN, a local area network, we could use Manchester encoding to tell if a packet was going by and thereby avoiding a collision. And because the Manchester encoding was going on and off frequently, we could tell while it was off whether there was a collision occurring. So Ethernet then became CSMA, CD, carrier sense, multiple access, carrier detection. So those are the three, what we thought were the three key technologies: Gerald taps, Manchester encoding, and AlohaNet randomized retransmissions. And that was all done in 1973. And what we next did was put some protocol on top of it. And that's the next period. Let me choose that diagram. Now that's also in the Invention memo. This shows an internet of Ethernets that is connecting Ethernets together, in this case through a telephone link. And you'll notice in this diagram, we anticipated that someday we would get back to radio. We call this the radio ether. We chose the word ether, by the way, rather than calling the network coax net. We anticipated that there would be other media in the future, and so we needed a word that was media independent, and that was the word ether. And so the radio ether, this is where we claim to have invented Wi-Fi, but actually this was the Aloha network. And we were waiting for the semiconductors to make radio viable, which occurred 25 years later. After beginning to fill Xerox with an internet of Ethernets, I moved over to be with David Liddell in the Systems Development Division with the charter of commercializing these two technologies, namely Ethernet and the PUP packet protocols. The Ethernet was to be called the Xerox Wire. We later backed out of that. And PUP was to be called Xerox Network Services. So now let me tell you the three real things that Ethernet contributed. Not Gerald, not Manchester, not AlohaNet, but these three. First, Ethernet delivered packets to the desktop. Previous to Ethernet, what arrived at the desktop was ASCII characters created by a Telnet protocol running in a time-sharing system. But Ethernet brought those internet packets all the way to the desktop so that you could write programs that communicated directly with the internet. The second key contribution of Ethernet was abundance of bandwidth. The day before I got Ethernet on my desk, I had a Texas Instruments Silent 700 running at 30 characters per second or 300 bits per second. And the next day, with the installation of Ethernet, I had 2.94 megabits per second. And if you do the arithmetic, that's a speed up of 10,000 times. And so after Ethernet, bandwidth became abundant. And then the third contribution of Ethernet is that Ethernet joined the movement, the internet movement towards standards. So you'll hear of Ethernet, TCP, IP, Telnet, FTP, HTML. So Ethernet joined that movement. And prior to that movement, protocols among networks were all vendor specific. And then following the move to SDD to be with David and to commercialize Ethernet and PUP, I left Xerox to start 3Com Corporation on June 4th, 1979 to commercialize Ethernet and Internet and to begin the standardization process which marks the end of this particular session. So with that, I think I'm done. Back to you, Geoff.
Well, I thought we were going to hear a little bit more about the start of the Xerox wire than that, but we can move to Dave to do that. Mr. Liddell.
Well, we're covering a period of time, 1975 to 1980. And during that time, I was basically the child vice president of system development, in that I was only 30 when I started doing that. The Xerox Corporation was at the peak of its powers at that time, owning a big and rapidly growing market. But the chairman, Peter McCullough, knew that it wouldn't last forever and that we wouldn't cut down trees forever just to have office memos and so on. And so he made a wonderful statement, which was that he wanted Xerox to be the architects of information. And this was very useful because you could justify doing almost anything under that particular rubric. Now, what I'm going to talk about is about Ethernet. This is not the story of how Xerox completely transformed the computer industry, which it most certainly did, nor is it about the internet, which has had enormous impact. I'm only going to talk about the Ethernet, but you need to understand that it was only a small part of what we were doing. As was mentioned earlier, we were building the first graphic workstation. We were building the first laser printers. We were the first to use a client server architecture rather than a host to host architecture. So this was a lot of new stuff, spent a lot of money over a number of years, and Xerox boldly let me do it. However, it was complicated inside Xerox. And this is part of what I want you to understand. We've never really talked about this publicly very much in the past, but when you think about it, Xerox was a company completely founded in intellectual property and secrecy. That is, they were the only guys who could do what they did. They had an extremely strong patent portfolio, and that was their method of operating. And they defended that portfolio like mad. They sued several big companies very successfully. They were, in fact, so successful that the Justice Department told them, hey, take it easy, boys. You know, there was a consent decree because we had this quote monopoly power conferred by the patents. Now, saying in the middle of that environment that you have a technology that's unique to you and you have patents on it, namely the Ethernet patents, but that you're going to share it very reasonably with other participants. By reasonably, I mean not at a low price, if any, was a shock to the system.
So David, I believe Xerox was the first company, and you can correct me if I'm wrong, that ever got taken to task for a monopoly granted by a patent, because patents are in fact designed to grant monopolies, but we were too good at it. Is that correct?
Yeah, that's basically right. So I'm going back and forth to corporate headquarters, making the argument that says, I know what you want us to do. You want to feed the printers that only we can make. And to do that, we need a workstation that lets glorious multi-font documents be created easily, and that allows us to produce line drawings and images and other things. And other people will recognize this, and they'll come after us to compete for the workstation business. We want those competing workstations to have to print on our printers. And that's not going to happen unless we publish open specifications for how to do it. This was a period when IBM had been sued by Telex, and many companies were wanting to maintain closed proprietary networks and interconnection protocols, downloading the microcode to their devices and so on, so that competitors couldn't squeeze into their theoretically closed network. So taking a different tack than that turned out to be extremely attractive to the customers that I went out and talked to. They weren't getting anything yet. We were just talking about the Ethernet and what it would be able to do. There were some complexities, not only the ones associated with convincing people in Xerox that it was okay to license this openly and that would be good for us. I also had to show that we could not, with Xerox's cost basis, make a standalone business of just selling networks. That is, we couldn't, if you will, be 3Com, just selling interconnects. It wasn't going to suit our financial model. It cost $100 to enter an order at Xerox. So it was kind of hard to sell fonts for $40. Huh? But the real point being that I had to show that it was the sleeves out of our vest to get other people to use Ethernet and to leave us eligible to capture their printing and storage business. Xerox was rather a large player in storage at that particular time. They owned Century Data Systems and Diablo and Sugar. And they sold a lot of storage products. And so the idea that storage should be easily accessible on a network rather than hooked directly to a host was also a new idea, but a very attractive one to the potential customers. Now, this did lead to some other things that had to be dealt with. Xerox had bought Scientific Data Systems, which in its day was a really good, high quality, first class company making mini computers essentially that were used for scientific purposes. Bob Spinrad, the VP of software there, had, while working for the government, kind of invented the technique of automatically run experiments and so on. And so they had a good footing in that market, but also in simulation and other things like that. It was bought very expensively at the peak of the Xerox stock value. And within a few years, they were really struggling. digital turned right around and kicked their ass. I mean, it was scary to see what happened to the quote mini computer part of their business. So of course, the natural reflex, I'm sorry to say, was to say, oh great, well let's go challenge IBM then, and try and make a more general purpose data processing product. And that didn't go very well either, as you can imagine. That had mixed effects for the future of the Ethernet. It made some people very frightened of anything to do with the computer business and just saying, let's stick to Lightning, LIMS, copying, okay? Also, there was a big computer room printer made by Xerox. Very, very beautiful product, actually, 9700. And PARC had done the design of the logic for it. But we OEM'd a PDP-11 from digital, which was part of this machine. Well, that scared people. I thought, oh, DEC's going to learn all our xerographic technology. And, you know, it took a long time to get people down off the ledge about that. And the printing systems division was always very afraid that we were somehow giving away their future. More about that later, perhaps. Intel, on the other hand, was selling us lots of 8080s, which were going in copiers. And, the Electronic Operations Division down in Los Angeles was buying a lot of 8080s. The old fart that ran that division got really mad at me because I was meeting with Intel without bringing him along, not that he would have understood what the Ethernet was about, but nevertheless, I got taken to the woodshed over that. And there were lots of those kinds of barriers. So intellectual property phobia, watch out for DEC, don't you mess with our relationship with Intel, and so on and so on. But they did have this document called the OIS Task Force Report. It had been done in the early 70s. And it said Office Information Systems will have a terminal called a PageMaker and something called a Xerox wire to connect it to printers. Now, there was no technical detail at all in this. And most of the people on the task force weren't technical anyway. But that was there in the archive, so to speak. And so, much so we liked that quote Ethernet unquote, to avoid a big fight, we just in the operating plan and the long range plan, I just referred to it as the Xerox wire that had already been enshrined in this task force report. Now that brings me to how did we ever get this done? Because Xerox had all these competing internal activities. IBM had just started a company called SBS for Satellite Business Systems. So Xerox, which had many IBM executives in it, thought, oh, we ought to have one of those too. And they started a thing called X10, Xerox Telecommunications Network. It never went anyplace, but they felt that they ought to have sway over any kind of networking. And we had another group there that said, no, we need to be in the telephone business. Okay, we ought to have on-premise equipment, what do you call those damn things? Private branch exchange, PBX, stuff like that. So there were some competing groups that had to be vanquished as well. But the long-term idea of a network with sufficient data rate to capitalize on graphic workstations and laser printing was the item that we could sell, combined with the fact that it wasn't a standalone technology from which we could make a lot of money. So that kind of is the basic business dynamics behind the process that we went through. When you have a big successful corporation like Xerox, it has a staff for everything. Meaning, you know, I had a corporate technical staff and a corporate strategy staff and all this. And these guys were very annoyed that we just weren't consulting them or getting their sign off on anything. And then Fuji Xerox wanted us to let them sign off on this approach. And a professor in Japan had written a paper called, or written a patent actually called An Improvement to Ethernet. Now this improvement, instead of using the binary exponential backoff with a shift register and randomized, it calculated a hyperbolic cosine function for the backoff interval. And of course, this was ridiculous, you know, at that time. The logic to do that would have been monstrous, but the Fuji Xerox people didn't know that. So I had to put out that fire too. Finally, in the midst of all this, Bob Metcalfe and I were very close friends, and people knew that. And I had put Bob on a list of exceptional fast track people. And when one of those people leaves, then there's a big investigation. I wanted to know, well, why didn't Metcalfe leave? You know, what did you do this? Did you do that? Did you provide him this or that opportunity and so on? So I had to go through a lot of that. And then after he left, he started to he helped me by not really helped me, by writing to my boss and saying, well, I put together this thing with Intel and DEC, you know, and you ought to pay me for that. Well, Xerox management hadn't even known that I was involved in this. So then they came back after me one more time and said, David, this guy's your friend. Did you put him up to this? Is he, you know, is there some deal here that you didn't tell us about? So once more, I had to go back and kind of explain and justify and so on. Nevertheless, I give Xerox great credit. They were taking a big risk, spent a lot of money on the whole office information system, but they were willing to let the central piece of it, the Ethernet, be used as an attractant to our printers. And that was very bold. By the way, at the same time, they were being the patent cliff had gone by. They were being set upon by both IBM and the Japanese. And by God, they beat them both back. Okay, and survived both in the high end of the copier business. So this was a time window in which Xerox wasn't Ethernet wasn't the most important thing in the world to them, and they still let me do it anyway.
So, Dave, was our lack of low-end printing engines a big problem?
It depends a little bit on what you mean by low end. That is, we did have, what was it, 3,300 or whatever. There, we did in SDD work with Webster to make a low end product because you couldn't use the 9700 grade ones or even the 1 page per second versions like
Dover.
Right, like Dover. So, but we did get this nice little, you know, kind of office desk side copier and got it properly outfitted and drove it with the right software and everything.
But it was built like a lease machine with all aluminum castings, like our big machines, and got knocked off by all the injection molded stuff that came out of Canon.
Sure. I mean, you can only do so much, and Xerox had the very problem that the auto industry and the computer industry had, which is we don't want to give sanction to the compact car, mini computer, or desktop copier, because all of those are low margin products, and we own this market. And so if we don't endorse it, it just won't go anywhere. And that was obviously completely wrong. So, I mean, I love Xerox courage and their willingness to support research, and I think they did a great job. They weren't perfect, but they came out of that. It's a good landing if you walk away from it, and they did okay.
So is it now time to turn things over to Gordon to say how a big computer company can't make mini computers? It seems like a perfect transition to me.
Fine with me to start. I'm going to kind of reminisce in three time periods. One is leading up to meeting Bob Metcalfe, who I regard as the marriage broker for DEC, Intel, and Xerox. And then the second period is that period where the three companies ended up with a specification, and then the famous Blue Book, which we're going to hear a lot about. And then the third period is the beginning of a commercialization, which was marked by the press conference at the World Trade Center in 1982, February 82, with Dave Liddell and Bob Noyes. And actually, I think Rich was there too, or Bob Hawes was there from digital. So anyway, that first period is important to really reminisce of what the situation was there. And that really, DEC had introduced the VAX computer in 1977, October 77. And I was out selling that in actually Japan and China, and then Australia. And then on the way back in the summer of 78, I stopped for 3 months or 3 weeks in Tahiti and was scuba diving and had nothing else to do but to sort of think of where we should be going from digital's perspective, and came up with the idea, let's do the IBM 360 bit. Namely, let's have only one computer and we'll bet everything on that. That's the Sun has said that too, with essentially one arrow or one bow and lots of arrows or whatever. But anyway, the essence of thinking of that 3 weeks of thought was that we're going to bet the whole farm on the VAX architecture, because we had several machines in design, including a VLSI chip, and that we're going to have those all one architecture, and that single architecture. By the way, we with an environment like that, we needed to have a way to connect all these computers that we were going to sell with this strategy, because unlike the 360, our strategy was thinking of the computers in a hierarchy, that there were. DEC was, quote, a departmental mini company, which said that you bought a mini computer and you connected dumb workstations into that, either by dial-in or by hardwire, where you got dumb terminals to be up to maybe 100 kilobits per second. That was done on a time-shared basis. And DEC had been a pioneer in time sharing. So the middle level was this departmental thing. And at the higher level, we're building computers that would interconnect together as a mainframe, quote, IBM competitor or so. And then at the lowest end was the emerging idea of workstations. So that was kind of the environment, and it was called the VAX strategy. And so I was busy selling the VAX strategy. And one of the components of that strategy, or I'd say maybe the key component of that strategy, was that somehow we needed to interconnect all those computers together. So that was the idea of, we knew what was going on vis-a-vis PARC and a local area network. So we had local area network efforts within digital. In fact, one of the spinouts was Dave Nelson, who founded Apollo, which was a distributed workstation environment that was competed with Sun. So that was kind of the environment there, and as we moved in, and I was busy selling the bet it all on VAX strategy, and that was through the winter of 1978, and then in January 1979. Meanwhile, Sam Fuller had been meeting Bob Metcalfe, and so I met Bob and said, "Gee, yeah, I didn't have to say it, but you turned out to be our savior, because everything depends on being able to have a fast, beautiful interconnect." And so we'd like to be a part of it. How do we become a part of that? And how do we get your patent, basically? And because I had, in a former life, had been a advisor to an MIT or IBMer who had explored ring networks, and then there was a ring network by Soderbergh, and who was out hawking his patent. And so all I knew is we didn't want to have anything to do with ring networks. So so after meeting, Bob penned an email or a letter for me that went to the vice president there at El Segundo, Campbell, who was headed Dave Liddell's boss, and George Paik, who was head of research at PARC, and said, "Hey, let's work together." And the upshot of that was that the DEC Xerox was starting to work on the patent on the spec. That all got going by March of '79, and then along the way, I had I'd say one of the first face-to-face or video conferences with Phil Kaufman of Intel, where we agreed that Intel would come in as another partner as and would be there to coach us to see how that would all play into the chips to support an Ethernet, a full-blown Ethernet server. So I'm not going to talk about that period until we actually announced with this press conference in January of '81. I'm sorry, January of '82, which was actually 3 years after essentially the start of our meeting and being there, and shipments started after that. I'll comment a little bit about the World Trade Center meeting, which was we all presented, and I think at least Dave Liddell recalls one of the good quotes that came out of that was one of a woman from Business Week asked, "Well, how are you going to compete with WangNet?" And I said, well, first off, there's not a lot of corporate cable running around in corporate environments. And secondly, the problem is like a sewer, that in principle they carry water, and we carry water mains and the sewage and probably the gas line there. But the problem is sorting it out at the other end. So that was one of the things that happened in the World Trade Center meeting. But nevertheless, we introduced it, and then and that was introduced furthermore a couple of months later in the Netherlands and also in London. And but in essence, that was the kind of genesis of getting together. So essentially, we had to have Ethernet. It was our whole strategy and success, and it turned out that it was true after that on the introduction of the products in actually our first products, I think, were in '83, which incidentally was virtually 5 years after my thinking about all this in Tahiti took place. And so from a drive, we were probably the most dedicated player in this whole thing, because we viewed it was our whole life ahead. And anyway, I think let's hear about that. The rest of us are going to hear about that interesting period from agreeing to have a get together to the crew, who we're going to hear from the crew who actually took it from that period to the time when they were. In fact, I'll just quickly, let me go over this a second here. Let's see, I wanted to do do you get me sharing there?
Not yet.
Let's see. Okay. Zoom. Let's see. Thought I would be so. Okay. Okay, that, by the way, I'm sort of colorblind here, so I'm having trouble. I said share screen. Is that coming up?
So after you say share screen,
Yeah.
it should pop up a new window.
Okay.
And then you have to select a screen from that window. And then you have to click share in the lower right corner.
Okay. How does that look?
Yep.
Got
You
it.
made it. Congratulations.
Okay.
You're a quicker learner than I am.
Okay, and then I need to go down here and say, let's make that a little bigger. I think okay. Anyway, this was the environment in 1970s of a time-shared computer with dumb terminals. Here, I think these were PDP-11s there. And then the VAX came out and really had the market there. I'd say a solid market for 5 years as a time-shared computer that ran on VMS and also Unix versions of Unix in October '77. And this is, it was a year later that the VAX strategy had come into play. And here's the famous dumb terminals that we all used. That was a VT100, which was 2,400 to 9,600 baud, particularly if you were using remote. Now, here is the strategy. When Bob came, we said, Bob, we want you to be part of the computer interconnect task force. And that task force had three components. One was this, this was the product strategy that the board adopted in January of '79. At the same time, we were meeting with Bob. So there was a thing called the CI, which was a high performance link that connected VAXen together and with PDP-10s and had a big file computer. And then the thrust of DEC's business was this intermediate level, which were time-shared minis with running VMS, VAXen VMS, and various other versions of or DEC operating systems, Ristas and RSX were all run as time-sharing systems with VAX. And then at this lowest level were these personal computers, which we saw PC clusters coming. But remember, this was 1970, January 79, and the IBM didn't take over the piece as a PC until until 82 when it was introduced. So there was this three-tier, we viewed computing in this sort of three-tiered fashion, and that was the beginning of the interconnect. So the CI was computer interconnect, NI was the network interconnect, and then at this lower level, we had a thing called the BI, the bus interconnect, was how you built bus-based computers, which was a successor to the Unibus. So essentially, in fact, I viewed Ethernet. This was at the World Trade Center. I viewed I said, here's some of my slides. Ethernet is a unifying key to the 5th generation because it's a standard really for interconnecting computers. We were trying to really address this terminal interconnect problem. These were RS-230, or these were all twisted pair connections that went to terminals and things in a terminal room in an installation. Here's what an installation looked like without it. Ethernet. It had all these computers, and DEC had a thing called DECnet, which was a forerunner to TCP/IP that was done by interconnecting computer and doing all of the switching within the computer. So one of the things we wanted to do was to relieve the switching load on those computers without having to introduce the ARPANET IMP. I saw no reason for IMPs when you can just use the computers themselves. So, and that's how we did. We interconnected those. And then with Ethernet, I saw, oh, it's going to look like that. Very nice. Get rid of all the switching that has to be done in the computer. And then here's a VAX in the background. There's a terminal here, and there's a terminal a BT100 over here. And then here's the famous yellow cable that carried Ethernet.
Well, in particular, going back to that picture,
Yes.
It's sitting in an empty cable tray.
Yes. Yeah. The beautiful thing was we reduced the load by having faster interconnect. We could either telnet as we had always done, or we then had essentially telnet computers which you built to do all of the terminal concentration that would then be carried over the Ethernet. And so essentially a whole bunch of things happen here with it, but we had high-speed communication, really simplifying the wiring, and we're providing offloading and then incremental growth without having to take the network down as you reconfigured. And so it kind of looked like this with computers and network and users connected that through this kind of simple structure. So anyway, let me stop there.
Okay, so now you convinced us of the use case at the time. Maybe we can go back to Dave and John Shoch and talk about how the proposal was received within Xerox to open it up, and in particular, open it up to DEC, and who else was on the horizon. John, you want to lead off on that?
Well, I think I'll actually pass it off to Metcalfe and Liddell. So as I said, a lot of my work was at PARC, and Bob had left by that point and was working from the outside, and Liddell was in the product organization so the center of gravity, I think, was with those guys. And Bob, you might want to talk a little bit about how you wrangled some of the parties to the table, and David talked about some of the internal politics, and you guys might just elaborate on how you got that across the finish line. And then at some point, we will have to bump into the elephant in the room, which is the IEEE.
David, you want to elaborate? You're muted. Or shall I?
Now you're off.
You go ahead, Bob.
All right, so I had left Xerox and was consulting for Digital Equipment Corporation for Sam Fuller. And he invited me to participate in this interconnect task force, which met periodically at a hotel overlooking the Mass Pike out in Southborough, I guess it was, one of those places. And this task force, so I was the facilitator of the task force, and we developed a long list of interconnects, and then afterwards it was greatly simplified, as Gordon has just shown you. And I met with Gordon in Building 12 in February of I think it was Building 12, isn't that HQ? And he asked me to build, my recollection is, and I don't want to, make stuff up, it's been a long time, but my recollection is that he invited me to design a new network. He really liked Ethernet, and he wanted me to design a new one for DEC. And I said I couldn't do that because I felt loyalty to Xerox, and plus I had already designed the best network I knew how. So Ethernet would be the answer. So we, in that meeting, decided, well, let's approach Xerox and partner on Ethernet rather than try to engineer around them. And so I drafted a letter. Gordon sent it to, I guess you've already reported, Mr. Campbell. I thought it went to David Liddell, but I guess not. Well, it obviously ended up on David's desk, right? Campbell wouldn't consider it without showing it to you. And then, so how did Xerox decide to accept Gordon's proposal?
Well, that's a little bit of what I was talking about. That is, I did have to make as it were, a business case for doing it. There was some fear of digital and somehow losing control of the printing technology. There was the difficulty that Xerox lived by patents, and most of the patent attorneys were not in favor of doing this. They thought, now we've got something other people want, and we ought to take advantage of it and make a business of licensing it and so on. I did not believe this would work. And I explained that all you do then is create an incentive for somebody else to come in and do some other thing. I do remember that there was a lot of discussion when I insisted that You want a license, you can have it for only $1,000 and we'll give you the documents and the data, but you have to run at 10 megabits and you have to be compatible. Otherwise, your license is void. And people from Zilog, they're quite upset about this because Carico wanted something that would run at 100 kilohertz or something like that. And they said, well, okay, well, I guess we'll have to take you to court then. And the Xerox patent lawyers just said, make my day. They were just so anxious, to sue somebody with this good patent. So the internal discussion was, you might say, a little bit fearful. I mean, in other words, they were just saying, well, have you thought of everything? I mean, is there any way that this can go wrong? Or, how could we be hurting ourselves here? And will we have to give up anything or agree to not doing something? And I said, no, it isn't like that. And then Intel wanted, I don't know how many people here remember the Intel blue box, but the blue box was essentially a computer, a terminal from which you programmed microcomputers. So in other words, it was a sort of a human accommodated thing that you could sit at and had a decent keyboard and all that. And you hooked up your 8080 or 8085 or whatever it was, wrote the program on this blue box, which then downloaded it and so on and so on. Well, Intel wanted to be able to use the Ethernet for that. And I said, well, there's no reason that you can't use the Ethernet for that. Yeah, but we don't think we need all these specs, I said, no, sorry, I'm not going anywhere on that. The performance level has got to be fixed.
Hey, David, can I tell my version of the Intel story?
Please.
Sure.
So I got a contract, I3Com got a contract from the National Bureau of Standards to write a piece on the impact of standards in the world. And by the way, that contract never got completed because they were a slow pay. And they pissed me off by not paying for my first invoice. So I never submitted the final draft and they never did pay the first invoice. But while I was there arguing with the National Bureau of Standards, I was sitting down in the waiting room and there was a guy sitting next to me and I introduced myself and he was an Intel guy and he had showed up at NBS to see if he could find a standard for their new chip technologies. They had some new NMOS thing. And I pitched him on Ethernet while we sat there in the offices of the National Bureau of Standards. And then when he got back to Santa Clara, he arranged for me to meet a guy named Phil Kaufman, who promptly introduced me to Andy Grove. And then they arranged for me to do a seminar there for their engineers, and I pitched them again on Ethernet. And then that was just before June, and they were beginning to show interest in what became DICS. So I immediately founded 3Com. That is, I concluded that since Xerox, DEC, and Intel were about to work together on Ethernet, that maybe I should start a company that would serve and leverage that market. So that's my version of the Intel story. But I think there are two other versions of the Intel story that I've heard glimpses of already.
Well, I'm interested.
At least one in which IBM was sort of annoyed by all this DEC, Xerox, Intel stuff and started pressuring Intel not to prioritize an Ethernet chip, but to make this HDL or SDLC chip that IBM wanted for, you should pardon the expression, SNA. And so there was some pressure there, and Xerox had a bunch of IBM executives in it. And they called up David Kearns just to say, what are you guys going to do with this? What's going on here? What's this deal? David Kearns said, look, we'd love to have you guys be in on this, or at least have you use it after the joint work is done. And they wrote us a polite little letter, as I recall, saying, well, we think Ethernet is a very strong design and we'll probably plan to be compatible with it, but we have to meet the constraints of our 3270 terminals. And basically it was just a synchronous 32 bits every mumble microseconds that had to be delivered. So I never knew too much more about how that went, but I did know that they were squeezing Intel kind of hard.
David, can I have a little more on the IBM War story?
Yeah.
So the way I remember it, they had Bob O. Evans. Bo Evans was a senior
Right.
guy at IBM, and he reached out to some of the ex-IBMers at Xerox. And so, I'll have to get the time frame here. And we had gone public with DICS or the Ethernet when we were in the token ring fight or whatever. And
Right.
so there was this meeting set up in Palo Alto, and I think you and I were there. Redell, were you there?
Yep.
And so these guys showed up, and they're very smart. We knew some of them: Paul Green, Carl Kummerle, Werner Bucks. These are guys who've done token ring. They'd written a lot of papers. We knew them, and they showed up, and they had this is my memory of the meeting, which is probably wrong, but it's my memory of the meeting. And it went something like, and they had this huge meeting, and we're sort of there pretty casual, and like, sure, ask whatever you want. We're here to share with you. And they said, well, and they had a spokesman who had clearly rehearsed all the questions. And they said, well, we have this constraint. Can the Ethernet do that? I said, oh yeah, no problem. We do that all the time. Well, what if you have this constraint and this constraint? Oh yeah, that'll work. What about this constraint and this constraint and this constraint? You might want to go run an experiment to do that. And then it was like, and we finally figured out this is all about terminals, really small packets, really high speed, really fast response time. You could add a whole new box, but you couldn't add any buffering. The thing was like,
Right.
Can you do this, 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 this? And we said, no. Why on earth would you ever design something like that? And one guy elbows the other and says, yeah, see, I told you have a stupid design. And we're just going, okay. So my question is to everybody on this call, I would love to know what happened to the trip report written by IBM after this meeting. And if anybody's got the files, because half of them maybe went away and said, yeah, the Ethernet's the right answer. And the other half said, no, we need the token ring. We've created a justification for it. And man, I would love to see the trip report from their side of that meeting.
So IBM contacted me, and they offered me 2 consulting gigs, $2,000 each, Franklin Lakes, New Jersey, and Research Triangle Park, North Carolina, to pitch Ethernet to 2 rooms full of engineers. And I want you to know I won the argument in both cases, but I didn't get the order. That is, I was not an experienced salesperson, so I didn't know how to sell, so I lost that order. Just imagine what life would be like if that sales thing had gone through and IBM decided to adopt Ethernet. Wouldn't that be amazing?
I don't think so. I think it would be I think we would be amazed at their demonstrating their capability for screwing things up the way large corporations can screw things up.
Yeah, it didn't.
Well, the fact is they ultimately
it didn't please them when I referred to their network. I referred to their network architecture as SNA, and they didn't like that.
Well, they did eventually go with Ethernet, like Rich was saying.
They went with Ethernet 10, 15 years later.
Yeah,
exactly.
When they decided that they would go in the workstation business and run Unix, with also when they finally decided that they could do Ethernet. But it's hard from here, where here means both this year and Silicon Valley, to remember what the environment of those big successful technology corporations was like back then. And by the way, Intel wasn't such a big corporation either. It's a few $100 million. I mean, it wasn't trivial, but it was nothing like Xerox and IBM and so on. And all these decisions had 1 million people signing off on them and 1 million questions being asked and all that sort of stuff. My own feeling is that we got very, very good support from the senior management that had come from IBM. Dave Culbertson and David Kearns and those guys, they got it. And they were really supportive of us. Xerox other executives mostly came from Ford. And there was a big emphasis on financial management there. And so there was a complex process called phased program planning that guaranteed that every product program took at least 4 years, if not longer. And that required various sort of box checking, laborious tests and so on. And the person who saved us from all that was Don Massaro. He had been the boy CEO who came in and saved Shugart, and the Xerox bought Shugart, and they put him in charge of the memory products group, which owned those 3 companies. And he was getting a little bored and restless, and they sent him down to Dallas to take over a division, which at that time was kind of a turkey farm. You know, I mean, it wasn't really that productive or that great. And he really whipped that place into shape. And they told him he could have a free hand to do what he needed to do, but they needed to see results pretty soon. So among other things, he just told me, well, do you want to go through this phase program planning thing? I said, no, it's not necessary. We know so much about how these things are used, and this isn't a, slipshod design or marginal. He said, okay, well then just tell them to go away. Just tell them to go to hell. We're not going to do it. I said, oh, well, okay. And then there was this Xerox wire thing, and he said, I thought you called this thing the Ethernet. I said, well, yeah, the Ethernet is the original invention and the thing that we use at PARC and that we had in the White House and all these demonstration places, but that's the Ethernet. And the Xerox wire appeals back or refers back to this OIS task force. And he said, that OIS task force was all bullshit. And why don't you just go back to the name Ethernet? And I said, you won't have to ask me twice. And so we immediately went back to Ethernet. He agreed to untrademark it so other people would be able to refer to it as Ethernet and so on. I mean, he was a warrior for us, I'll tell you. He did a very good job.
So can we talk a little about how we actually got collaboration down at the technical level now that we've got the macro agreement on getting together on all of this? There was implementers who had to do spec writing, and they had to actually talk to each other, and getting that done was no trivial task. Let's see. Bob, you wouldn't be a good one for that. How about Mr. Redell?
I can say a few words about that. I mean, the other participants have done a great job describing the environment in which all of this happened. I'd just like to comment on maybe a couple of misunderstandings about how the Ethernet, quote, emerged from Xerox PARC, as we say in the title of this session. So there are a couple of extreme ideas that are really misunderstandings. One is, you can at least read it in parts of, for example, the book Triumph of the Ethernet. There's this idea that sort of floats around that the 3-company DIC's effort basically took the ideas from the 3 megabit experimental Ethernet and then did sort of a blank sheet redesign for the Blue Book version. And of course, from everything that's been said today, it should be obvious that the 3-company process was a continuation, technically, of work that had been done on the Xerox wire effort, right, been going on for several years.
No, so, I tried to give the impression that the early development of the 10 megabit was done at Xerox.
Yes, right. And I mean, I don't think that these misunderstandings I'm talking about are things that have come up today, but rather just things that I've detected in the larger discussions around the community about this. And there's another opposite extreme, which is that Xerox just designed the Blue Book Ethernet, and DEC and Intel were just brought in to provide sort of added market impact and help us into the standards world. And I mean, that's really wrong too. From the very start of the whole Blue Book effort, DEC and Intel provided a lot of really crucial technical input to the design. And the result, I think, is much stronger than what we could have done alone. And I just wanted to mention a couple of examples of that. From DEC, Rich Siefert in particular brought some really, really deep experience with the characteristics of signaling on coax. And he wrote the key Blue Book chapter on the physical layer. In one specific thing that he contributed to, and maybe we can say some more about this, is some key insights on how collision detection should work on the coax. And from Intel, the Intel representative to the sort of spec troika, Rob Ryan, brought in an idea that I think was really excellent, writing the definitive specification of the data link layer as a textual algorithm. I'm using that word rather than computer program because it obviously wasn't really a program designed to run on a computer. But even though I was actually the one who ended up writing that specification in Pascal, I really have to admit that doing it that way would really never have occurred to me if Intel hadn't pointed out that they were adopting that approach because it was really helping them specify their increasingly complex chips. So I guess those are just
Dave, I can add to that, Dave. I think we were the first to write a formal protocol specification in what was essentially a computer language, and with good reason. I mean, we had to make sure that people who didn't speak English as a first language could go into a closet, read the spec, and build a compatible product without the ambiguities of human languages. And by definition, computer programs they must be unambiguous.
Was that Gordon Bell's ISP?
Well, I can point to Geoff, and Geoff will remember that I almost single-handedly delayed the adoption of Wi-Fi 802.11 for exactly that reason, that they had specified a very, very complex wireless access control mechanism in English prose. And there was no way to know if you complied or not. And so they went back and formulated their protocol. And to this day, to my understanding, all 802 standard protocols are done either in a state machine formulation or a computer language or something unambiguous, something not human language.
To reinforce your point, Rich, the original specification of 802.11, I believe, was done by somebody who was Dutch. So we had the native speaker problem there.
Yeah.
I mean, certainly, I did the Ethernet patent. And at that time, you couldn't patent software.
Right.
So I had to translate the design of that Ethernet into all hardware, including all the microcode and some of the software in the Alto had to be converted into hardware in order to get it patented. That's a little bit like translating into out of English or Dutch.
Yeah, that whole issue about, was this thing a computer program? I mean, it looks like it because it's written in Pascal, but that's really not quite the right way to look at it. That's why I referred to it as a textual algorithm. I mean, that Pascal has concurrent threads running in it, but there's absolutely nothing in there that represents best practice in doing concurrent programming. It's all this very fussy manipulation of shared variables in a very careful way. And I mean, you can imagine if you took a multi-threaded program with mutexes in it and gave it to a hardware engineer and said, why don't you implement this? The first question would be, what the hell is a mutex? So this really wasn't designed to be run on a computer. It was really designed to unambiguously, as Rich said, specify what in the world this thing was supposed to be doing. And there was, in fact, English prose, and there were also flowcharts that were describing all this, but it was very carefully stated in the spec that the algorithmic specification was the determining spec if there was ever any perceived ambiguity between the three. So anyway, I just wanted to say that the process, these are just two examples of the process that happened in the room when the three of us were just hammering out the final blue book. And I've got to say that process was long, and sometimes it was kind of bumpy. I mean, we didn't just all sit down, smile at each other and start singing Kumbaya. There was a lot of what real diplomats like to call frank exchange of views. But in the end, I think the Ethernet spec was much stronger for that. And so even though there were some sort of heated discussions, I look back on it and I'm really glad that I had the opportunity to play a role in that.
I think it was important also organizationally that there were only one of us from each of the three companies that were allowed to hold the pen, so to speak. And,
Yeah.
Everyone in the company, had ideas, but we didn't have 400 people in a room like IEEE does. We had the three of us.
Yeah, I absolutely agree with that, Rich. And I think also it was appropriate given this sort of asymmetry of the history where Xerox had been working on this stuff for 7 years. And we brought in a couple of other companies that had tremendous technical expertise, but didn't have that 7-year background. I think it was quite appropriate that David Liddell actually chose me as the representative, because I was not one of the people at Xerox who had 7 years of background working on the Ethernet. And I think that sort of made the process for the three of us pounding this thing out a little bit more symmetrical, which I think was good.
Yeah, and I was brought in not because I had, great expertise in computer design or computer networking. I didn't, but my background was in radio communications and transmission lines and signal integrity and electromagnetic compatibility, and that ultimately made the physical layer of Ethernet robust. And one of the real problems with the competing technologies at the time, things like ArcNet, or if you remember Corvus OmniNet, or some of the other ones, they were flaky as hell, and they got a reputation for being flaky as hell. And even if they ever fixed it, you never lose that first impression. So we have to make sure that when people put Ethernets in, they worked. And especially when you made 10 million and 50 million and 100 million of them, they worked. And yeah, we were beaten up a lot for overkill on the physical layer parameters, and overkill on the data rate, and overkill on the CRC algorithm. But in the end, that's what made it work for, what are we talking now, 60 years?
Yes, I do remember teasing.
Corvus was a
Well,
problem
cables.
for 3Com because they shipped that junk and spoil the channel. Then when we came along with Ethernet, they'd say, well, we've tried that already. That doesn't work.
Yeah.
So it was a problem for us.
Yes, I do remember Rich kind of teasing you about that quad shield cable, but you had the real data.
Which is hanging on the back of my chair, by the way.
Yeah.
So Rich,
I still use tons of this stuff.
right.
It's great for ham radio applications.
The discussions about collision detect have jumped back up and are occurring today, and all of the same arguments are taking place. So we're going to need some input from you on that.
Well, and that was one of the other key changes in the evolution from 3 meg to 10 meg to commercial 10 meg, was that the original Ethernet just looked for data corruption,
right,
as an indication of collisions, and that works most of the time. But most of the time, at least Gordon taught me at DEC, most of the time isn't good enough. All of the time, especially when you're shipping in huge volumes, and you don't want 1% of them to come back to field service, because when you're shipping 10 million of something, that's hundreds of thousands of things. So the DC collision detect was mapped out worst case, and it always worked. And so we just basically had two separate channels there. We had an AC channel for data signaling, and we had a DC channel for carrier sense and collision detect. They just both happened to be on the same cable at the same time.
We need to talk about that offline in a modern context. But
I'm fortunately still alive.
yes, yes, indeed, and still vocal. So let's see. Mr. Belleville, we haven't heard from you. Do you have anything to add to all of this?
Yeah, just a little bit. Yeah, I really want to give so much credit to that crew that Rich led from DEC's point of view, and Tom and Rich was part of that, and I think we had one other person. But that small crew that wrote the blue book, and that I think John was the editor of that came out, really deserves a lot of, I'll say, to me, all the credit for having a workable Ethernet. But because within digital, we had stories like that too. I mean, Ken Olson would love to work on physical problems, and he always said, I want to use a twisted pair. And we said, no, Ken, we're using, it's not us, it's those other guys. We've decided on this cable.
Well, but Ken ultimately was right. It's just that it took 10 years for the silicon to be available to be able to do that kind of encoding.
Well, then the question is,
and then, but keeping the group small was critical.
The question is, as it is today in the standards groups, how do you do collision detect on twisted pair without Manchester coding? And it's a tricky problem.
All right.
So let's see. There's some people I haven't gotten to at all. Roy, would you like to chip in for a few minutes?
Okay. What I thought of doing is slight switch gears, but I wanted to just tell a little bit more about the early Ethernet controller development that I worked on. And what this will also do is set some context for Robert Garner, who has some interesting stuff to show us. And it would be good if he could follow what I talk about with some of the artifacts that he has and some of the other feedback. I just wanted to mention that, we've heard the word Ethernet and Xerox wire, but when I started working on the development, the term Ethernet was used exclusively for the prototype network that was already running at PARC, whereas the Xerox wire was referred to the product that we were planning to ship with the Star Workstation, as its name became. And so in the early days, when you talked about Ethernet or Xerox wire, you were really talking about two different meanings and contexts. Of course, later on, we decided to rebrand the Xerox wire as Ethernet, and so that all became fuzzy again. But some of the stuff that I worked on included, these tasks. So the first thing I worked on right away was the finishing the documentation of the Xerox wire specifications. There had been an early draft that Bob Metcalfe had created at the end of '76, and so I pushed that further. We created a first version published in June '77 and a second iteration in March '78. And these are the second two columns on the table you showed at the beginning of the meeting. And these transitioned later into the formal Ethernet specs. During those specs, during the development of the specs, we worked decisions that had to be made. One that's been mentioned was the planned network speed. Would we go with the 20 megabits per second that we had planned, or
down to 10. So during the spec work, there was a lot of work done on these various issues, including that one. And I think Robert will say a little bit more about that. And then there were other issues such as collision detection functionality to be implemented, and the controller data path, should it be half duplex, full duplex? I don't have time to go into those right now. After the specs were completed, then we turned attention to the design of some actual controllers. And Robert Garner and I worked on the development of these controllers, and we really talked about 3 different iterations. First, I want to mention that the plan at that point for the Star Workstation product was the D0 or Dolphin machine. So that was what we had available to test this Ethernet configuration, Ethernet and Xerox wire. And so all the early work was done on that D0 machine. So for the initial testing, the first thing we designed was a 3 megabits D0 Ethernet controller. So that enabled us to test the concepts that we had on the Ethernet on the existing network that was already running at PARC. For the product configuration, we actually completed 2 designs, one at 20 megabits per second and a 10 megabits per second Xerox wire controllers. But then the decision was made to select the 10 megabit speed. And so we never actually implemented or built the 20 megabits, but just the 10 megabits. And so what we did next was we proceeded to prototype, build the boards and prototype them for first the 3 megabits and then the 10 megabits. Just out of interest, we had a very rapid turnaround technology to build these boards. It was called stitch weld. I'm not sure if that's used at all anymore in the world. And so we first tested the 3 megabits configuration, and then we tested the 10 megabits configuration. At that point, we pretty much had the early system running, and many of the design decisions had been made, for example, the network speed. And at that point, there was a decision made to not use the D0 machine for the product machine. And then we started building the Dandelion machine, which eventually became the Star Workstation product implementation. At that point, I actually transitioned to the development of another part of the Dandelion machine, the I/O processor subsystem. But Robert, however, continued to work on the Ethernet controller development, following up the D0 work, and he proceeded to design the Dandelion-based Ethernet controller. So I thought that was just a segue to tell you all the different objects that we worked on at the time. And let me turn it over to Robert, who I think will show you some of these actual artifacts and maybe talk a little bit about some of those technical decisions in more detail. So Robert, do you want to keep going?
Doesn't Bob Belleville have some artifacts as well?
Yes, he does actually, but whoever, I know Robert has some waiting to.
Why don't I go next?
No, just go to Robert. Yeah, definitely go to Robert.
Yeah. All right. So we're going to have a little fun now. You guys, this has been incredible background, but let's get down to some. So you start with a cable. This is the Xerox PARC, right? The 3 megabit cable. And to which you put in a Gerald tap, which Bob Metcalfe referred to. You'll see there's a little hole right there. You take the Gerald, manual.
We need to
drill, but you put it into the hole. You rotate it.
We need to mention that was stolen from cable TV technology.
Yes, I'm going to talk about that. Yeah, this whole idea came from Dave Liddell, who had a summer job basically working on installing CAT TV cable systems in schools. And so at PARC, when Chuck Backer, who was also a ham operator, by the way, suggested that the ALOA broadcast and media could go over cable, Dave Liddell chimed in and said, "Oh, well, who wants to, like Bob said, who wants to take a cable and have to cut it and add a connector to it, and then have to do that twice because you have 2 ends to connect to a BNC T? Why not instead just use this CAT TV approach?" So you you drill in, and it works really nice. It's really easy to do. You take the drill out, you tap it, just to make sure there's nothing in there, and then you take the transceiver that's been designed by Tat Lam. Tat Lam was a premier analog designer, a contractor to Xerox PARC, who designed the monitor analog electronics and used to work at Tektronix, and he was an analog guru. You just kind of screw it in like so, and then you take your drop cable, which is going to go over to your personal computer. By the way, the Alto, we've talked a lot about the Alto. They cost about half the price of a home in Palo Alto at the time. And each of us had one. Talk about Xerox giving us lots of money. You take the transceiver cable, you plug it into the transceiver. You hope that you can still, the latch hasn't been screwed up by somebody. You snap it. And you take your up to 50 meters of transceiver cable and hook it up to your Alto. Remember that at the time we've talked about, you've heard mentioned twisted pair. Well, the twisted pair telephone closet wiring cabinet was owned by AT&T. So it's not like we could put a giant rack of electronics in there and start using their twisted pair. So, but you could install this cable though, anywhere you want. So that's the cable. But let me talk a little bit about some more artifacts here. So this was the Alto workstation itself. We all had one of these on our desk. 0.5 megabit black and white screen, mouse, a 2 megabyte removable disk pack. So you could, have these lined up on your desk, and you could plug these into any Alto, so you didn't have to sit at your own Alto all the time. Your environment came with you, kind of like a SneakerNet virtual machine. Half of the main memory, by the way, was dedicated for the display. What audacious people they had there to actually take half of all memory and dedicate it to the display. So here is the.
Well, it also meant that anytime you did something compute intensive, the screen had to go blank because it needed the memory.
Not all the time, but that was not an uncommon trick. Sometimes the bottom lines of the text editor would disappear. Bravo, Charles Simone's text editor would disappear to get more memory. So here's the first, actually this is the second Alto board designed by David Boggs and Bob Metcalfe. Bob projects himself as a businessman, but hey, he was a real technical dude back then. This board has about 60 chips in it, but it doesn't tell the whole story, because the microcode that Bob wrote to do things like the binary exponential backoff algorithm and moving the data from the Alto memory to the small buffer here on the card, that's written in microcode. So to run that microcode, well, you needed a 16-bit ALU, and here was the 16-bit ALU card from the Alto. The 8008 from Intel, wasn't really capable of this level of performance, and so this ALU card multiplexed all the I/O devices through it: the Ethernet, the disk, and the display. And if you probably couldn't run all three at once, but that's just the ALU card. I mean, you needed to store the micro instructions somewhere, so you had this double control store card to hold the micro instructions. We're getting up there. Now you can see why it cost half the cost of a house in Palo Alto. And then you had 17 of these memory cards that used the 1 kilobit, 1024-bit dynamic RAM chips from Intel. The very first dynamic RAM chips that came out. This card actually was also used in what was called the Max time sharing server, which had the largest single installed base of DRAMs in the world at that time, 18,000 DRAMs in one machine. So a small number here, 17 slots of these. So all these things are what it really took to get that Ethernet card to run. I said I didn't want to say too much more about the 3 megabit net, except to show you, the transceiver that Tat Lam designed. There's 2 little cards inside it. There's one side, and here's the other side. The way one of the key functions of Tat Lam's transceiver was to compare the signal you were about ready to send onto the wire to what you were just receiving. And if they differed, that was a collision. What more simple thing could you ask? And, it's true that Rich made it more robust and strong. But this seemed to work. Bob Metcalfe at the time was designing the next level protocol called the PARC Universal Packet, or PUP. And in his specs, he was saying, well, all these various networks, they might drop 1 in 100 packets, or maybe 1 in 500 packets. And John Shoch, in his performance analysis, showed that maybe 1 in 5,000 packets were being lost, and that was considered good. So, it's all relative. So
By comparison, here's a 10 meg transceiver,
yes, yes.
which had a few more components in it. And Gordon, I'm going to give credit to somebody who hasn't been mentioned, a great analog system designer named Jesse Lipcon. We used to joke, we call him Jesse the Lip. We said we needed Ethernet bandwidth in order to accommodate his the speed of his voice, because he could talk pretty darn fast. Yeah, this is the second generation showing the coaxial cable.
It was called the Battleship.
The so-called Battleship. Yeah, I've got the bottom of the Battleship.
Yeah, Rich, in Xerox, the speed of talking was measured in units of millilampsons.
Okay, well, as I said, we had Jesse the Lip, but yeah, this took a few more components, but this has triple redundancy on the wire and DC collision detect, etc. So go ahead.
And before I go on to the Xerox Star, this was also a cute little device that Tatlam and other companies came out with. You could plug in 4 transceivers and then connect to the cable. And this could go up to 16 transceivers at some point. So you could save a lot of, if you didn't like using the tapping tool, you could use some of these. All right, so let me now quickly move on to the Xerox Star. So this is the Xerox Star. It has about a 1 megabit display now. It's got an optical mouse, by the way, from Dick Lyon at PARC. It has, the Alto had 128 kilobytes of main memory. This guy had up to 384 to 512 kilobytes of main memory. It was the product version of the Star, but what Roy mentioned was that we actually first, bless our hearts, we designed, Chuck Thacker designed, and Brian Rosen designed its predecessor, and this is about what it looked like. It was called the D0. And we decided not to ship this for the Star because it was a little too expensive and maybe not that reliable, but they kind of cleaned it up. You have to go, Bob?
I do.
Okay, thanks for joining us, Bob.
Thanks very much.
Yep.
Thank you so much, Bob.
I would say, speaking of the Star, I have the original Ethernet spec masters on Star floppies,
Which I will then plug into the Star as soon as it gets working.
which I can pass to you, and you can plug into the Star.
Okay. So the other place the D0 showed up in was this 5700 copier. So this was the first major copier from Xerox, which had the laser in it, laser printer. Well, 9700 did. This was the second, but it also had a scanning station, so you could actually scan documents, store them, and print them. You have this on your desk now for several $100s. This system in today's dollars would set you back $300,000. 5700, and in here was where the D0 electronics were located, with compression boards and decompression boards.
My Canon, which I bought 7 or 8 years ago, cost me $125.
That's a big difference. So Roy mentioned that Roy and I co-designed, I don't have a big actual card because they're as rare as chicken's teeth, the D0 Ethernet card. This is the section that was designed by Ron Crane, who is our analog expert. Ron Crane also designed the complete memory system and display controller for the Dandelion, which is a much more difficult task. But this card had both separate transmit and receive sections, so it was what we call full duplex, which was kind of odd. I mean, I'm glad that Bob is off now, because for some reason he wanted us to do full duplex controllers, even though the network itself is half duplex. It only has a packet on it at any given time. So why on earth would you waste all this real estate? Well, it made it expensive. So in fact, when I went to the Dandelion, we went back to half duplex, which is what the Alto design was like, that David Boggs and Metcalfe had designed. So very few of these were actually shipped. But to show you the prototype technology that Roy mentioned, this is the prototype board for the D0 Ethernet controller. And, you know, for whatever reason, this technology was kind of fun. This was the stitch weld technology. A big machine, semi-automated machine, would just draw straight wires and a human operator would weld them to a point. You could then rip off wires and put them back on so you could quickly turn the design. I'm not sure this helped us design better systems because you could just easily change it so quickly. But this is the design where what happened is that the guys in the former scientific data systems people in El Segundo told us for a 4-layer printed circuit board, we had to reduce the number of chips. We had 160 chips, full duplex designed for the D0. And to fit it on the 4-layer printed circuit board, it had to be 120 chips. At this point, we thought we'd go 20 megabits per second. Hey, we have 10 fingers and 10 toes, so that's why Bob wanted 20. I was just thinking, but he was pushing for 20, even a higher number, but we couldn't get the chip count to fit on the board. So I found a 10 megahertz CRC chip in the Fairchild catalog, same one it turned out David Boggs had used on his board. And I went to Bob Metcalfe and said, Bob, now it all fits. And that's how the Ethernet came out at 10 megabits per second. It could have been 20. All our tables could have been 20. This is the Ethernet controller for the Dandelion, now half a board. I covered over part of it because this was the other half of the board was the interface to the laser printer, the low-speed laser printer. So this is about 60, 70 chips for a half duplex Ethernet controller. And again, though, that's not the whole story because you have to have a CPU. So here's the Dandelion CPU card with the control store, the 4 kilo word 48-bit control store and the 2901 base CPUs. You know, what I like to say about this card is that you replace the control store, which held the micro instructions, with cache. You take the CPU, make it 32 bits. You take the instruction width and shrink it down to 32 bits. You get a RISC board. You get a RISC you get a RISC processor. And that's basically the transition between the CISC world, microcode, which was good for I/O, microcoded instructions, wide, microcode, and the whole thing that swept the whole computing world, which was RISC computing. And I think that does it for me, but just in case you thought we were done with the Dandelion, a little later we came out with the 6085, the Daybake processor, which I think Geoff worked on in 1985. And after that, the IBM PC really took over.
I did, but the 6085 used a fully integrated Ethernet controller. So,
yeah, we don't have time here to talk about all the chip development. I'm working on a history of the first 10 years of the Ethernet, and I'll include in that all the great work done by AMD and MOSTEC on the so-called Lance controller. Seek did a chip that Bob used on the 3Com board, and of course Intel did a chip which eventually people put on motherboards. But all that history we can save for a future webinar, and certainly will be in my book.
Okay.
Robert, it seems like one of the key things that you mentioned was the change from 20 megabits down to 10, and specifically in terms of that CRC chip. I sort of had the impression at the time that change was made that there were other issues, including various aspects of signaling on the cable at 20.
Yeah, so yeah, the second vote was from Ron Crane, who was concerned that the 20 megabit size would create too much noise on the cables that would defeat some of the collision detect circuitry. Now, if we had Rich's approach, maybe that would not have been an issue, but with the approach we were taking, and there was even concern at the time that Rich's approach would work. Rich had to kind of prove it. And I think, Rich, you didn't say you did this great analysis with a giant Fortran program and spreadsheet that you submitted for your master's thesis.
Yeah, well, yeah, that was more proving out the numbers and figuring out how much the margins are. And yeah, but that was done. This is a spreadsheet that was done back in DigiCalc, which was like a VAX version of VisiCalc, which predates even, Excel or 123 or anything like that.
Right. Well,
okay, that's it for me, Geoff.
We're only a half an hour over our allocated time, so I think we better at least take a look at the questions and answers. So,
Well, let's give Bob Belleville a chance if he wants to say anything. Bob, you
Yes.
want to say anything at all?
yes, please.
Sam, I'm also very sensitive to the fact that this is 2 hours in and we're going to lose our credibility here. I went over to Apple. And so I took it from, if Gordon Bell took it from mainframes to minis, I took it from minis to personal computers. And that was where the big numbers game was. And I can tell lots of stories about that, but I think we should save that for some other time.
Well, just one.
You want to mention your Cub design as well? You tried to rattle the.
I tried, and I don't know if David is still on thing, but I built an 8086 Alto, basically called Cub, and that's what evolved into Daybreak that you just showed. And then I went over to Apple and did the Macintosh, so it was a step way down from even the Cub.
So
that's what we needed to get the millions of users that were really going to need the network.
So to get the cost down for the Macintosh, you went to an existing communications controller that wasn't Ethernet compatible. What speed did it run at?
I think it was 256K. It was just the UART.
Yeah.
It was just the serial thing. So we did a transformer connected multi-drop 2-wire network, and that was AppleTalk. And I never intended that to be the end all and be all of things. My actual idea was that we'd eventually switch over to ISDN because the phone company still had a powerful role, and that was their high-speed star-connected network. But unfortunately, they were so tied up with their ideas that it was never going to materialize. And so we then could switch out to Ethernet after, whether it was a decade or 15 years later, and now everybody's happy.
Bob, if I remember right, I think I gave you an award, an Opie or something, for your work on Cub. Isn't that right?
You did. I think you gave me $2,000. And I have a picture of the machine if we want to show it. Is that okay?
Sure.
Are you on? You can see it?
Yeah, that's our team to start with.
That's the Dandelion team.
I'm on the left.
And I'm.
So there's the Cub. The box here is the whole thing, 8086. I think it had 128K or maybe 256. This machine also had handling for voice, so it could be an answer machine and handles telephone. It also had a page scanner, so you could scan pages in. Then here is the back panel, and you notice right here, there's a hole where the network connection is supposed to be. And I was really in need of that single chip controller for whatever network we were going to use. I really needed that to be on this because I didn't have anything like the amount of space in that machine for the board that Robert just showed. And at Apple, it was purely a matter of, I didn't really have any choice. I had a $10,000 laser printer that needed to be shared. And so I needed a network to do that. Didn't cost anything at all. So the total cost of my interconnect to the laser printer was only $50. The materials cost was only about 10. And that got the whole world thinking about things like desktop publication and all kinds of things that led to the now ubiquitous computers that we all have. And I'm sure, I also want to say, actually.
Hey, Bob, can I add something to that? If you hadn't have put these ideas in Steve Jobs' mind, they may not have happened.
That is correct. I also put them in Mike Murray's head, and he went to Microsoft and put them there. And so that's how that happened. But I wanted to really say something to David that's here still with us. And your presentation just reminded me and expanded just how complicated your job was. And I am not sure I was helping.
No, you were a spark, Bob. I mean, that was a really good thing. You pushed everybody. I remember you sent out a memo entitled "People Must Do More." Okay, and I always appreciated that. So if you didn't make my job easier, you certainly made it better.
Also, we can tell that very quick story about having Dave House from Intel in to have a cub demonstration. I don't know if you would remember that. I was running it on an RS-230 link down to an Alto in the other room, just ran the cable through the hallway. And I was doing what you saw on this picture, just drawing on the screen. And he said, "How did you do that? What graphics chip are you using?" And I said, "Oh, I just use your CPU." And he said, "That can't be done. My people tell me it can't be done." So the world was changing so fast. The other thing we should be really clear about with all of our audience that still managed to stay with us, the world was changing so fast then that nobody should pretty much criticize anybody's decision about anything, because the ground underneath us was changing faster than a California earthquake.
Indeed.
Now you take the questions.
I'm trying to field some on the fly here. Many of them are mostly comments that aren't really questions.
Well, we have this one. Someone said they're not clear about how Metcalfe got Intel and Xerox to contribute to the Blue Book. Did DEC or Intel ever build a 10 megabit per second prototype and test it prior to that? Who wants to take that? Rich?
Seems like that would be a Rich.
Yeah, can you say the question again?
It's not
Are you
clear
asking
how-
if we built a prototype Ethernet before
Right,
getting
prior
together
to-
with Xerox?
Prior to the Blue Book, or at the same time as the Blue Book? And how did
Well,
Metcalfe?
yeah, of course, we prototyped the Unibus controller.
But that was after
during
the
the,
DEC. That was after.
while the standard was being written, we were prototyping the Unibus controller, and we did a gate for gate emulator of what ultimately became the Lance chip. Hundreds and hundreds of chips
From
doing
AMD and
the
Mustang.
gate for gate emulation.
Yeah, from
Yeah,
AMD and
gate for
Mustang.
gate emulation. But yeah, of course, we prototyped everything before we built it.
By the way, Brian Berg here. Take note that Dave House from Intel is indeed part of this current conversation. So he would have heard what Bob Belleville just said.
Nice.
Thank
Okay,
you.
Yeah, we were sort of writing the spec at the same time we were designing both the channel and the algorithm. So you tried to keep up with each other.
So many of the questions aren't real questions.
Well,
I have a question. I have a question, actually. I've subsequently learned, what I think I've learned is that actually the British invented the idea of packetization at Bletchley Laboratories during the war. Does anybody know whether Bob Metcalfe or Dave Boggs actually knew about that, or was that they just did it in parallel?
Well, I think they knew about packets based on their work on the ARPANET. You know, Bob Metcalfe, as he mentioned, designed.
Well, this was way before that.
I know, but we'd have to ask them whether they knew about the British work or not.
Well, actually, I think the person to ask about that would be my friend, the Brit, Aidan Paul, who was the designer of the first integrated 10 meg coax transceiver.
I see that Aidan Paul is also one of our participants today.
Goody. Aidan, you
He probably can't speak.
No, I guess he can't speak.
Yeah,
But
I think that's all that prehistory, Bob. We might cover in another webinar. You know, we kind of stayed away from the foundations and early history because that's another whole 3-hour webinar. if
At
that's
least-
okay.
as you can see, no shortage of material.
Tom Gardner can elevate anybody to be able to talk if so desired.
Okay.
Uh,
Okay, well, let's see, Larry Macinder asked, could you say more about the role of standards above the physical layer? Hal, do you want to speak to that? XNS and PUP? We don't have Bob here anymore.
The PUP stuff never got standardized. It was just, you know,
No, he wants to know, he wants to hear about it, not that it got standardized, but just about it.
when I got there in '76, PUP was alive and well in PARC. The Altos were running BCPL stuff. In addition to the hardware being primitive, the software was primitive. I mean, there wasn't what we think of as an operating system. You didn't boot the operating system. You booted a shell, which then, you know, booted a program. And if your program didn't crash, it, you know, rebooted the shell when it was done.
Well, it's time, Hal, it's time to talk about Junta, which was sort of the operating program, except that when you fired up an application program, you blew it away. And then,
But my role was to translate all of the BCPL stuff into Mesa, and the rest of Liddell's group was building an operating system to go with that. And when they got the hardware running on the D0, I had the software all ready to go, and we ended up using the D0s as gateways from the 3 megabit world to the 10 megabit world. And the thing that's missing so far is that whole crowd was addicted to having printers and file systems out there on the network. We had plenty of traffic once the hardware was ready.
right, the big contribution of Altos and the 3 megabit Ethernet is that everybody was addicted to the environment.
Jeff, could I leap in a little bit?
Of course.
So just to provide a little context on the PUP, XNS, and a few words about TCP, you know, the way I think of the phase in here, there actually was a pre-Alto, pre-Ethernet phase, which is, you know, data general novas, the MCA, a parallel bus, some file transfer stuff on the MCA, sending to printers and XGP. And so there was a sort of little mini period there before you had the Alto. Then you have a period with the Alto and the early Ethernet, and there's a handful of Ethernet specific protocols that were not internetwork protocols. So it works on one Ethernet, which ran through the whole building, had 8-bit addresses, and there was, you know, XPrint and EEFTP, and there was a chat program and a couple other things. But while the Ethernet hardware was just coming up, there was a parallel effort on, okay, we need, you know, if you could look ahead beyond the one building with one network that had 20 or 30 machines, how are you going to connect together a bunch of these? And this was at a time where internetworking was in the air. There had been some meetings, there were some discussions, there was early work at Stanford, there was early work in Europe. Metcalfe sat in on some meetings at Stanford on TCP, and, you know, we sort of, you know, Bob in particular ran out of patience. I mean, everybody said, we need something. We can't wait for Vint and his group. And so PUP was done. And, you know, PUP is basically the first internet, although there's some complicated history here and relationships. And one of the key things is it was a pretty good impedance match, because you had the Ethernet with 8-bit host addresses, and you had PUP, which was designed with an 8-bit network address. Would there ever be more than 256 networks? And an 8-bit host address, and that all sort of worked together pretty well until one particularly pathological day. And I think I saw Ed Taft on the list. And so I don't know if we can enable him, and he will correct me on this story, but there was a day where everything sort of stopped working right at PARC. And we had the large Max was the shared machine for file storage and some other stuff. and everything's got flaky. And you know, what used to happen is people would step up from their cubicle or out their door and go, something wrong, what's going on? And we scratched our heads, and Ed Taft and Dave Boggs did most of the debugging, and they were looking at the wire and they're trying to get a connection, and you get back 2 answers. And it said, one said, yeah, connect. And the other one said, no, you can't connect. And like the software is completely confused. What's going on? And I think it was Taft who looks at Max and says, no, Max is sending 1 packet. And it's like, where's the other packet coming from? And it finally, we figured out somebody had been on a different PUP Ethernet in a different building and had picked up their machine and moved it over to PARC to debug something. And we had 2 machines with the same address. And this is an oh shoot moment. It's like, oh my God, you move a machine from one network to another and you haven't coordinated the address space, and you've got network relative address, and you are in deep pucky. Hit the reset button. And the guy who deserves the credit on this, I mean, I think he's also on the call, Jogan Dalal and Bob Prentice, with I think a suggestion from Will Crowther, and I'm sorry, Jogan, if you can correct me, about, oh no, we need to take an operating system idea of unique identifiers for files, and we're going to have a 48-bit unique identifier over all space and time. Everybody thought, and talk about audacious ideas. This is an unbelievable concept. You're going to waste 48 bits. You're going to index a table that's 2 to the 48th long. How are you going to find anything? But if you want to have your laptop go from your home to your office and not have to reconfigure your entire world, you have to solve all this. So the guys, you know, at SDD, so PUP was done mainly at PARC. SDD did what was called XNS. It is an amazing combination of, again, an impedance match between the 48-bit address on the 10 megabit Ethernet and 48-bit addresses in XNS that solves this problem. Now, you know, those of you who are in the TCP space, this doesn't get addressed until, you know, first of all, you got to split TCP into TCP and IP, which we lobbied for and finally help them see the path to that. And it's not until IPv6 that you start to correct the addressing problems that are so there's a long-winded answer, but you know, there's a series of iterative designs at both the network level and the internet level to make all the stuff play together.
And John, I wanted to add the comment that in PUP, the byte stream protocol was equivalent to TCP, and the datagram protocol was equivalent to IP. Is that correct?
Yeah, and I mean, as I've talked on this before, and everybody knows my point of view, is that the original design of TCP was an integrated design that only brought out a reliable byte stream. And we kept pointing out that if you're doing page level file access, if you're just trying to get the time of day, if you're trying to convert a name to an address, you needed page level access at the equivalent of an internet packet. And the original TCP didn't have that until Rev 4. And I was at the meeting where it finally got split, you know, and it was not just me. I mean, Danny Cohen on behalf of Packet Voice, he said, look, I don't need reliable byte streams. I just need to get some packets through and get some voice. So it was a very complicated series of decisions. And we were blessed. I mean, you know, David said about some of the positives of big companies, as frustrated as we might have gotten, you know, you had a team that was focused. We didn't have a giant design committee, and you tried something and if it didn't work, you tried something different.
I heard a wonderful story on the 48-bit number. The manufacturing guys freaked out because they were going to have a separate set of documents for each workstation because it was different.
I have heard that story, and I don't know, you know, I mean, I believe part of the conversation with Intel, and I wasn't there for it, so maybe Redell or somebody else will know, was, you know, oh, by the way, an Ethernet controller chip has to have a unique number in it, and therefore you have to figure out at the time you make the chip how you're going to program a number into it.
Well, and the answer to that for many years was the way you made a controller was without the address. And the address lived in a chip, which was a 32 by 8 ROM. And you only had to worry about the part number problem with one 16-pin DIP. But the rule in Xerox distribution for part numbers was form, fit, or function. And so if they had separate addresses, yeah, you at the board level, tracking it would have been.
Well, somebody pointed out that they didn't have problems with serial numbers, so they could solve this problem too.
Yeah.
Well, the other thing about that address in the chip, as opposed to coming from someplace else, is you really wanted to make the controller chip, even if it had its own address built into it, you wanted to make it possible to change its mind about what its address was in case you had several chips on the same machine and you wanted to use the same thing for.
Yeah, and actually the reality is the chip specs, if you go look at all the Lance chip specs and Intel chip spec, it's all a parameter downloaded into the chip. And
Right.
we actually made it in our microcode in the first boards as well. So, you know, we hardware designers have a way around these kind of edicts.
No,
And
generally,
I know at DEC they had the same issue, and I think Rich, you told me, or somebody told me about a story where they had two controllers with the same address at DEC.
in general, the chips always had an onboard address. They just loaded it locally from
Wherever.
a ROM in an
Yeah,
adjacent socket.
at DEC, we would create the MAC address as a function of the DECnet address. So it was sort of backwards.
Where did the DECnet address come from?
Human administrator.
Oh,
That ultimately changed.
Yeah, scaling.
All righty. Well, have we gotten through everybody?
So there's another neat piece of trivia on the software side. When you're debugging a machine, as you bring it up, it's typically a pain in the ass to get the disk controller going. And what you really should do is debug the Ethernet controller first, because then you can just download your software over the Ethernet to work on the disk controller.
Well, and that was what they did with what Boggs did with Dicentra.
Which Hal worked on, Dicentra.
It didn't need, as I understand it,
It didn't have a disk, so that was
it
the.
didn't have a disk, but it had a terminal port that could have been used for that, but never was.
Well, one of the great things about Ethernet as well is there were always these packets going around that you could download to get your system started with. And I sure wish things like Bluetooth worked that way.
Right. Breath of life.
Yes.
So I just muted everybody because the webinar seems to be drifting along. We got about an hour, about 55 minutes over, and a question did come up on the YouTube channel, which maybe each of you ought to opine on. The question was, did you ever envision the standards you created back then would evolve from a few megabits on coax to the 100 gigabits we see today? And so one at a time, you want to turn on your mics and answer it?
Well, I think I should try and answer that with my last slide, which I will try and put up.
Say one quick thing about that. I think in general, the answer is no, but there was work at PARC on an optical repeater, a very high performance optical repeater, so star repeater. So it wasn't totally out of the question.
We started talking about higher speeds fairly early in the game, and there were a couple of false starts before 100. But this is what we've been doing since then. If you look at everything but the last one on the right, we've done standards on all of this, and it all is compatible at the bridge level. That is, the packet format's the same once you go up the stack. So it certainly has been an established portion of the culture for a long time now. 1993 was when we did the 100 meg standard, and we had done, before that, we did a lower speed standard at 1 meg, which never went anywhere in the market. And we took a stab at doing a 20 meg, and there was no enthusiasm. And
another question that came up is, I find interesting, Ethernet is the interconnect that powers the modern age. Why doesn't Ethernet and Metcalfe Boggs spoken about in the same tones as telegraph and Morse and telephone and Graham Bell?
because they're not old enough yet. And
Anybody else?
I'm not sure it's quite as revolutionary. I think Ethernet is evolutionary, and it's surely a big step in evolution. And it's clearly, you know, an evolution that we've lived with now for 50, 60 years. But it's not like the first creation of computer communication systems.
it's not like the integrated circuit.
It's not like the integrated circuit. Or we're also celebrating today the 50th anniversary of the charge couple device, the digital camera.
Right.
That was fairly revolutionary, and that received a Nobel Prize.
But the inventor of the charge coupled circuit is not something that's known to the general public.
No.
The planar transistor in the integrated circuit isn't either, but it's closer. So, Tom, I think we have exceeded our expectations and we should quit while I think we're still ahead. Thank you very much. And thank all of our participants and all of our audience.
Thank you guys very much. Appreciate it.
Yeah, thanks for all the hard work.
It's been great fun.
Thank
And
you too.
a really big thank you for Tom Gardner for making sure that things could come off with so many people on this Zoom event. So thank you very much, Tom, for your guidance.
Oh, likewise to Tom.
Yes, indeed.
This is the biggest one of these events we've had. Thank you guys a lot for everyone who participated.
So I think that is time to end the meeting and the webinar. It's been a really interesting experience. Thanks everybody for participating, and thanks all of our attendees. We still have over 100 listening on the Zoom and on YouTube Live. This will be edited and become a permanent record on YouTube Live. Again, thank you all and have a great rest of your day.